So, we have calculated the Tc, we have calculated the Tc, it is related with the exchange this interaction dipole interaction energy constant lambda, right. So, now B m is equal to lambda m. So, so if I calculate B m molecular field and that I will get lambda. What will be the lambda? Then 3 kb Tc divided by n mu effective square, right, and into m. So, this for spontaneous magnetization, so its maximum value it can be in spontaneous magnetization, saturation magnetization. Okay. If it is maximum value, can take a saturation magnetization, because as I told that when alpha tends to infinity, then Bj equal to 1, so m equal to ms, okay. So, ms value n mu effective, right, m mu effective. So, from here what you are getting, Bm equal to 3 kb Tc divided by mu effective. Okay. So, if you calculate the this molecular field for say iron, ferromagnetic material, so its Tc is around I think 1043 Kelvin is Tc. So, if we take just approximate 10 to the 3 Kelvin, and if you take J equal to half, means only you are considering spin, not this orbital contribution. So, so then it will be mu effective will be basically equal to mu v. Okay. So, you know the mu v value, kb value, Tc if you take this, and then Bm equal to, then effectively for this condition this Tc by mu v. If you put all these value, this Tc equal to 10 to the power 3. So, it gives approximately its I think its field in the order of 10 to the power 3 Tesla, in the order of magnitude this 10 to the power 3. Okay. It comes around 1500 Tesla anyway. So, we are taking it will be 10 to the power 3 Tesla. Now, 10 to the power 3 Tesla is a huge, very high value, because in lab we use electromagnet, and now maximum magnetic field from electromagnet we get, it is 3 Tesla, only 3 Tesla. Okay. From electromagnet in our lab, from electromagnet. Okay. And using the superconducting magnet, nowadays one can get say maximum around this 30 Tesla field. So, in lab it is very difficult to produce even 30, 40, 50 Tesla. Say it is not possible to get more than 50 Tesla or say 100 Tesla. Okay. So, we cannot generate magnetic field in lab more than say it is 100 Tesla, right. But here internal field it is 1000 Tesla, more than 1000 Tesla. So, it is huge field, it is a huge field. So, now question is this, from where this field is coming, this internal field from where it is coming. So, that is the question, and answer is the way the Weiss considered as if this molecular field this originates from the dipole-dipole interaction, magnetic dipole-dipole interaction, and magnetic dipole-dipole interaction it's that if you one can calculate, if taking the distance, it depends on distance. So, this the dipole interaction, that energy it is I think it's inversely proportional to that energy is inversely proportional to r cube dipole. Okay. That energy is dipole-dipole interaction, that energy is proportional to 1 by r cube. Okay. And one can show that dipole-dipole interaction it's hardly it can give around 0.12 Tesla, 0.1 Tesla, okay, or within 0.34 Tesla, this dipole-dipole interaction it can give equivalent magnetic field, okay, equivalent magnetic field. So, the way the Weiss field we consider molecular field considered and we apply the it is called this mean field theory, mean field approximation. This BM we have taken as a mean field approximation, means this all the dipoles they experience this same field. Okay. So, it does not depend on the location of this dipole. So, on the average all dipoles are feeling the same field. So, that is called the mean field approximation. So, whatever calculation we have done, that is based on the mean field approximation. Okay. So, point is that it cannot be this Weiss molecular field, it cannot be, origin cannot be dipole-dipole interaction, because dipole-dipole interaction, that is magnetic interaction, that interaction is generally very weak compared to electrostatic interaction. Electrostatic interaction, Coulomb energy, which gives Coulomb energy. So, Coulomb interaction, so that comparatively that is very high. So, there must be, it is not the dipole-dipole interaction, origin of this Weiss field, molecular field, it must be the electrostatic interaction, okay, Coulomb interaction. So, that is the point. Now, to explain that one, what to find out the origin of this molecular field, and its strength is very high, it is 10 to the power 3 Tesla in that range. So, to find out the origin of this, then Heisenberg. So, Heisenberg proposed one model, it is called Heisenberg model. Heisenberg model of ferromagnetism. So, it tells that it tells that this origin of this molecular field, it cannot be magnetic interaction, magnetic dipole interaction. There must be electrostatic interaction, Coulomb interaction, and that could be the origin of this field, or that could give this high internal field. So, so he, I think this is in Heisenberg model, there he yeah. So, he considered that in crystal, this whatever we are permanent dipole moment we are telling. So, so he considered that they have moment. So, that we are considering the spin moment, spin, okay, they have spin. Now, in surrounding, other spin is there, other spin is there. Okay. So, if it is ith spin, so if this is jth spin. So, if you take simple model, 2 electron spin, okay. So, this ith spin Si, okay, and another one is Sj. So, they will interact, okay, they will interact. How they will interact? So, basically if the position, so ith and jth electron, if they have they are in lattice, so they have position, okay, spatial coordinates, say Ri and Rj, they have spatial coordinate Ri and Rj, and they have spin part Si and Sj. Now, if you find out the this is now 2 electron system, and if you find out the wave function for this 2 electron system, wave function has to be this, since it is electron, has to be antisymmetric wave function, overall this wave function of this system will be antisymmetric wave function, right. So, now this wave function have 2 part, one is spatial part, another is spin part. So, one is spatial part, another is spin part, okay. So, two spin is there, if they are parallel. So, you will get S equal to 1, So, S equal to 1, this basically give triplet state, and it one can show, I do not know whether you are quite familiar with the quantum mechanics or not, but just believe me. So, this triplet state, so its spin part, its wave function is symmetric wave function. And if they are antiparallel, then S equal to 0, you will get singlet state. So, singlet state and that is antisymmetric, okay, antisymmetric. Okay. Now, to become this wave function in general, this is antisymmetric. So, it has spatial part and the spin part. If spin part is symmetric, so this has to be antisymmetric. So, overall it is antisymmetric, or spin part is antisymmetric, then this part has to be symmetric, then overall it will be antisymmetric. Okay. So, for this spin part, spatial part is antisymmetric, spatial part is antisymmetric, okay, and for this one it is antisymmetric. So, the spatial part will be symmetric. What does it mean? What does it mean? So, how this wave function is? So, this wave function is formed. Okay. So, it has basically, it will have two parts, this and this, and these two parts come from the exchange, okay, exchange in spatially as well as from spin part. So, if I just talk about the spin part, so if the states, it goes from symmetric, if it exchange, so spin both are up, if just exchange, so one is up and one is down, okay. If it exchange, then what will happen? When it will exchange, so it will go from antisymmetric to symmetric. So, simultaneously spatial part will go from antisymmetric to spatial part will go from symmetric to antisymmetric. Okay. So, here information is that spatial part, it is related with the distribution of the charge, right, it is related with the distribution of charge, right, and I have spin part. So, nothing to do with the magnetic moment of the spin direction is important, okay. So, whenever the change in spin, there is exchange between the spin, okay, there is exchange between the spin, okay, then simultaneously there will be exchange in the spatial part, means there will be change in the distribution of the charge, right. Okay. So, whenever the spin part is affected by changing, then simultaneously spatial part, charge part also its changes. Okay. So, thus this way, when the spin or whatever dipole way or whatever we are telling this, they interact with each other, because of that it is simultaneously it is getting the charge, that is their spatial charge, they are interacting. So, these are called exchange interaction, So, the energy, because of that this energy, exchange energy or exchange energy. So, Hamiltonian, in terms of Hamiltonian one can write. So, it was written for this, that Jij, one constant term, it is called integral, exchange integral, J is called exchange integral or exchange energy constant, So, this energy, that is exchange between S, because of Si and Sj. Okay. Now, this is for two electron system. Now, I have in my crystal I have many. So, and this exchange energy, this is taken as minus, one can derive this basically, and then for considering all spin, we can take I, summation over I and j. Okay. So, this is the Heisenberg model, for this exchange energy, which will show later on that this exchange energy constant is related with the lambda. It is related with the lambda. Okay. So, that means this difference between these two, here just we thought it is magnetic interaction, but here it is showing no, it is not magnetic interaction, it is basically electrostatic interaction, because charge is involved whenever this something happening with the spin. So, simultaneously charge is also changing, means interacting. So, that exchange, that is why it is called exchange interaction. If they exchange, okay, spin part is changes. So, simultaneously spatial part also will change. Okay. And yes, and this Jij, it is called exchange interaction constant or exchange integral. Integral, because here summation we are taking, so integral or exchange energy constant. Okay. Now, here, so this exchange, either they are now how they are. So, if it is ferromagnetic ordering, if ordering is ferromagnetic, so then this J I think Jij, if it is ordering is ferromagnetic, means parallel. So, this Gij is 0, sorry, greater than 0, and if it is anti-parallel, anti-ferromagnetic coupling, okay, Ij, so then it is less than 0. Okay. So, what does it mean? So, this exchange integral or exchange energy constant, So, here as I told that either spin part is triplet symmetric state, or it is singlet antisymmetric state. Okay. So, this system, 2 electron system or whatever this or this many electron system also. So, it has it will have 2 energy state, one is for triplet, another is for singlet state. Okay. So, if this energy is for singlet state it is Es, and for triplet state it is Et. Okay. Now, if it is exchange, singlet and triplet exchange, so one has to overcome this energy Es minus Et. Okay. So, during the exchange from triplet to singlet or singlet to triplet, okay, so this much energy is required. Okay. Expense of this of the energy due to this exchange is this. So, this basically and this basically is taken the energy, exchange energy, the difference between the Es and Et. So, this is the exchange energy, is taken as the exchange energy constant. Okay. Depending on the system, this energy state for singlet and triplet are fixed. Okay. Now, if any exchange from triplet to singlet or singlet to triplet, if any exchange occur, so then energy either increase or decrease by this amount. So, exactly it comes by this 2 half of that Je, half of that. So, this one can find out. So, one has to write the wave function, spatial part, spin part, form the antisymmetric wave function for the system, electron system. Okay. From there it comes. So, that I have not done, because it may be difficult for you, but this the exchange energy constant. Okay. So, difference between the singlet and triplet state. So, this exchange from one state to another state, one state to another state, singlet to triplet, triplet to singlet. So, this much energy is required for that system. Okay. So, now what is the meaning of that? That J E is greater than 0, okay. J I J. So, this is the average exchange energy if I take, and it is constant. So, in that case, so it is greater than 0 means E S is greater than E T, E S is greater than E T. It is positive means E S is greater than E T. I think I have written correctly. This is E S, that is the problem if you do not derive. So, you have to yes, yes, yes. So, it will be E S minus E T. So, E S will be, when it is positive, E S is greater than E T, E S is greater than E T. So, your energy, Hamiltonian means its energy, okay. Its energy will be negative. When this is positive, energy will be negative. Okay. And when this one is less than 0, this one is less than 0, means E S is less than E T, E S is less than E T, E S is less than E T. So, E S singlet state will be preferable. When J is negative, singlet state will be preferable. Okay. So, that means antiparallel configuration is preferable, and when J is positive, J is positive. So, then E S is greater than E T, means E T will be lower than E S. So, triplet state, that energy is lower. So, it will be preferable. So, ferromagnetic configuration, parallel configuration will be preferable. Okay. So, that is the significance why we take J is greater than 0 for ferromagnetic ordering and J is less than 0 for antiferromagnetic ordering. Okay. So, that comes from here. Okay. So, this Hamiltonian one can write minus. Now, you imagine that in so now in this case we are dealing with the spin part, but dealing with the spin part, anything exchange in spin part, automatically this special part will be involved. That means electrostatic interaction will be active, So, here you know that if I have ith one here, this ith spin, okay, ith electron. So, S I S J, okay. So, here basically jth one is here. So, this if I take other one, so S I S J now S I if I fixed one, that is here. So, now S J equal to 1, 2, 3, 4, 5, there are many. So, they are interacting with this, right, like for this configuration. Okay. So, what is happening? So, this S I 1, this is 1. So, it is interacting with this all others, right, that is indicated by the J equal to 1, 2, 3, 4, 5, right. So, in case of BM, here also we have considered this similar concept. This one So, whatever the rest of the things they have influence on it. So, that average influence we took as a molecular field, right. So, if I write this one J I j as is taken as a constant J I j. Okay. So, here one can write, I can write 2 sum over I is greater than j. Okay. So, just to avoid double counting, because I j. Okay. So, I j now if you go for same 1 and 2. So, 2 and 1. Okay. So, that is why so to just this double counting we are considering taking here, too. Okay. So, here now this I and j cannot be exchanged. Okay. So, whenever this I 1, so j has to be 2, 3, 4, 5. Okay. So, otherwise whenever I equal to 1, so j can be also 1. Okay. So, this double counting whatever here was coming. Okay. So, that taking 2 we have considered that exchange between I and j. So, this I can write so this I can write like this. Now, you see I have spin SI, right, this is SI. Now, so interacting with this one with the rest of the part. So, I can write sum over j Jij, okay, interacting I with j and this Sj. Okay. So, this is telling this all j with interacting with this I. Now, for all I now this is 1 and rest of the others are interacting. So, I can express this way. Now, I can vary this I, Okay. Now, this part what it is? This part some effect of the others on this. So, the BM was exactly same, effect of the others on this, that average field. So, this I can replace with BM, this I can replace with BM, Now, this is energy, BM is field. So, energy is mu V G I think this magnetic moment dot this BM, magnetic moment dot this BM will give the energy. So, I can write Gj, I can write, so this I can replace with BM molecular whatever this one, and then magnetic moment Gj G mu V, you write G mu V. Now, G can be, if we consider a only spin, G will be 2, right. I think I have to put Gs mu V, yes, I have to put Gs mu V, because here I am considering only spin. So, Gs mu V Bm, So, now that the spin I am not writing, because already the spin is there, right, already the spin is there, for that spin energy will be, I think I will write, if it is spin, energy is, its moment is mu v, its moment is mu v. So, mu v Bm, mu v Bm I can write, or just simply I can write, if forget this one, just I can write mu, whether it is mu j or mu s or mu l, whatever. Okay. So, that is the magnetic moment dot B, that will give you the energy. So, this I can write equal to minus 2 sum over I S I dot Bm, and that mu I can write here outside this constant, mu I can write here, right, mu I can write here. So, ultimately here what we are getting here, if you, so this is the my original things. Okay. Now, for considering this equivalent, this molecular field, I can write this one. So, from here is Bm is basically one can write from here I have to get but 2 is there. So, here I think I am missing 2, it 1 by mu v or mu 1 by mu, this will be equal to, this is same. So, mu are there, yes. So, sum over j j I j S g. Okay. So, this the Bm molecular field, and yes. Yes. So, just I am missing this sum, I am missing one, I am missing 2. So, this is the original concept. So, this I can break like this, I can break like this. Okay. So, what I should do, I think what mistake I have done, this will be equal to, now if I consider this one, so here this Bm field is that one. So, this field is now applied on all the spins. So, that has come from these others, the J1. Okay. Now, I am considering now where from J1 whatever coming, that we have taken as a Bm. Now, Bm interacting on this Si only, So, Si, so now whatever the spins are there, all are S1, 2, 3, 4, 5, okay. That Bm applied on that. So, here what I did mistake is that, so I have to consider this Bm field, okay, and that equivalent energy Bm field and equivalent energy is mu Bm Okay. Equivalent energy is mu Bm. So, that one applied on SI. Okay. Now, SI is varies as a I equal to 1, 2, 3 etc., whatever the number is there, and this mu dot B, the energy is minus mu dot B. So, that is why minus. Okay. So, this I am writing from the concept of this Bm. I have spin 1, 2, 3, 4, 5, that is given by I, and on this spin this Bm field is acting. So, energy will be mu V, okay, or just I am writing mu into that field, right. Now, that energy will come from all SI, all SI. Okay. Now, I am taking summation on this SI. Okay. So, this mu, this SI is there. So, that is why S already is there. So, that is why this if I write this mu, this generally Gj j mu V, right, since it is only spin. So, that is S is already G S mu V. So, this sometimes people write here G mu V. Okay. So, G S mu V kind of things, G S mu V, that is the moment into this Bm. Okay. So, for all S I, for all S I equal to this summation 1 stay. So, that will be equal to this one. So, now if you equate this one, then yes. So, that is why I was missing this 2. So, let me write 2 by G mu V. So, this okay. So, this is the relation between this molecular field and the integral exchange integral. Okay. So, just from here one can explicitly find out this this relation with the TC, So, here if I take now see, if I take this interaction, if I consider only that exchange interaction is effective among the nearest neighbor. Okay. So, J ever, and that interaction is average, if I J I J whatever written, if I write that is J E. So, that is with nearest neighbor. So, this distance are same. So, J I J, that will be same for all. So, J E for nearest neighbor. If I take J E, then Bm, and that is only for nearest neighbor. So, I can write this one. So, taking nearest neighbor, that is why J is same for all. So, I can write 2 J E, okay, for each pair. Now, if I have Z number of nearest neighbors, so I have to multiply with Z. Okay. For each one is this, for each this Z, that S, okay, divide by G mu V, divided by G mu V. So, that will be the Bm, and now this Bm we have taken lambda m, So, this lambda m, okay. So, then lambda equal to, one can write lambda equal to I can write lambda equal to by m. So, 2 j E, that is E exchange one, not that. So, Z S by G mu V, and this M S. So, this is I think lambda equal to this by this 1 by m. Okay. So, m you have to take m value. What is m value? So, n mu b, n mu effective, in this case n, I should now, this problem is taking whether I will take this yes. Yes. So, I have to take this m. So, m I can write n g s mu b, right. So, n is the number. So, for each one that is the moment. So, I can write this. So, from here I can get lambda equal to 2 will be there, j e exchange integral, then z it is there, divided by what you are getting, n. You see here you are getting, so SS will go, okay. N I am getting g square mu b square, g square mu b square, g square mu b square, right, g square mu b square. Okay. So, here this is the relation between this lambda and j. Now, Tc, what is Tc? Tc was the mu effective. Tc, what was the Tc? Whether it is there, Tc was this, I have to, Tc is that is, yes, Tc was, yes. So, basically Tc, what is Tc? Tc was n, I think 3 kVA stuff that I just, you remember n mu effective square, then lambda divided by 3 kb. Okay. So, C it was the mu 0 and this for Tc it is lambda. Okay. So, now you put this lambda value from here, that is 2 j e z by n g square mu b square, okay, g square mu b square, and then mu effective, you remember mu effective was, what was that? Mu effective was j square j plus 1 mu b square, right. So, basically here this mu effective was j plus 1 mu v, sorry, I think this was square, right. Yes. So, then Tc you are getting n will go, g square will go, mu b square will go, I will get j plus 1, okay, j plus 1, 2 is there, j e, this exchange do not mixed with this, z by 3 kb. Okay. So, that is the exact relation for between Tc and that between this and this. Okay. So, I think this is the Heisenberg model. From this Heisenberg model, so this we can find out the origin of this Bm molecular field, and that is basically coming from the electrostatic force, electrostatic energy, electrostatic interaction, spin part and spatial part. Spin part if any exchange in spin part, there will be exchange in spatial part. Spatial part is nothing but the distribution of the charge, right. It charge distribution, so affect the charge. Okay. So, that interaction among the charge, it is electrostatic in nature, okay. And that whatever the molecular field theory we consider, that is correct, but there just magnetic dipole interaction kind of concept was taken, but this BM is basically that we are getting from this Heisenberg model also, and there is a connection. So, this expressed in terms of exchange interaction, wherever is here dipole interaction. So, that exchange energy constant J and here this lambda, they are connected, and that connection we have shown, and Tc also in terms of exchange integral, exchange energy constant one can write. Okay. So, that is all about the Heisenberg model, which is very successful to explain the high molecular field, but result are same whatever the from Weiss model we have got, this here also will get the same result, but approach is different, approach are more realistic, and this Hamiltonian in this form is very useful for explaining the ferromagnetic property of material. So, I will stop here, I will continue in next class. Thank you.